Okay, how you guys doing? Everybody all right? So today we're going to go through a bunch of stuff. So we're going to go through Kelvin's circulation theorem again. We're going to go through it. I'm going to do it because there's not a recording from last week, so I'm going to do it the way Landau and Lifshitz do it again. But I don't really feel too bad about doing that derivation again because that was the last thing I did in class, and I did it kind of quick. So I'm going to do Kelvin's circulation two different ways. I'm going to do hydrostatics. I am actually going to talk about potential flow, which I said I wasn't going to, but I'm going to talk about it a little bit because it's cool. Let's see, what else am I doing? Let's see, let's write up on the sideboard here what I said I'm going to do. Let's do it over here, get that way. I don't care about this. So I'm going to go over questions from the reading. I'm going to show you guys the von Karman street, and I'm going to show you some cool pool vortex things. So we're going to start with, what's that?
Sorry, I was saying, has this board been here the whole time?
I think so.
Yeah, wow.
Then we'll do Kelvin's twice. Then we'll talk about potential flow. And then we'll talk about hydrostatics. And then we'll talk about steady flow. And that will finish up chapter 4. So we're going to try to get through as much of that as I can, which the more questions you guys ask, the slower I go. So keep that in mind. Ask questions. Okay, reading questions. I want to touch up on the reading questions from last time, which I forgot to do. Let's see. What is vorticity? So vorticity, and this is a question that we're going to have that you're going to kind of wrestle with a little bit. Vorticity is curl of V. So it's just the curl of a vector field. So you can bring all of the curl intuition that you have for what that means. But it is kind of like the fluid spinning around in little bits. And it winds up being an incredibly important piece of fluid dynamics, as we'll talk about when we get to potential flow and flow past a cylinder. So, but we'll talk more about it, and don't feel bad about asking that question again. Here, let me make that accurate. There you go. One of you had asked about the in the thermodynamics that he does. One of you had asked about the mu n component in the potential, this is the chemical potential and the number of atoms. So this only shows up when you're adding stuff to the system, which we're not going to do in this class. So in this class, the total number of stuff is always going to be conserved. So we could just call that 0 or a constant. Extensive versus intensive. Some of you had some questions on that. I did talk about it a little bit, but if you have more questions, ask more. Why is dP over rho equal to P over rho in an incompressible flow? I don't actually leave this open for, we can discuss this now. So this is one bit of the, when we get to steady flow that we use. So why is the integral of dP over rho equal to P over rho in an incompressible system? So I'll give you some hints. So in an incompressible system, d rho dt equals 0. Yeah.
So rho's constant, you just pull it out the integral?
Right. Rho's constant. So this is true. Also div V equals 0. That's the other thing that's true for incompressible. I just want to say that so that these are tied together in your head. So rho is constant. So rho comes out and you're just left with the integral of dP, which is just P. So it's just P over rho. Let's see, I'll talk more about second rank tensors. My notes here are insufficient. Past me was kind of being sloppy and I can't read what I can't tell what I meant. Yes. Lagrangian versus Eulerian. I'm not sure what the actual question was. So that's all I wrote down. An ideal fluid is typically, when we say ideal fluid, we mean that the viscosity is 0, so nu equals 0. Also, usually, PV equals nRT. So for ideal fluid, usually it's inviscid and an ideal gas. And barotropic just means this, or P equals rho to the gamma. It just means that P is proportional to rho, or thereabouts. The flow past the cylinder, I will talk about that. And then, okay, T, everywhere we have a T in this class, it's always temperature. It's never kinetic energy. When we need kinetic energy, that'll be K. And then one of you asked about sound waves in space. And you had started the question by saying, I know that sound doesn't travel in space. And I'm going to stop you there because there's lots of sound waves in space because there's pressure and density and temperature. The density is really low, but nobody actually cares. We'll get to it. I'll show you that the sound speed is gamma p over rho. And as long as the pressure and the density vary roughly in concert, this sound speed could stay the same. So in a cloud of molecular hydrogen, the sound speed is about the same as it is on Earth because the density is lower. But really, this is equal to P over rho is just equal to the temperature times K over M, so gamma. So the sound speed really only depends on the temperature. Yeah.
What's gamma?
Gamma is the adiabatic index. So when you have an adiabatic gas, P equals rho to the gamma. This is a constant, this is a relationship. And gamma is the relationship of the specific heat at constant volume to the specific heat at constant pressure. You don't need to remember this. This is just to tie it to thermo. So gamma is just, for most of what we need, gamma is just this bit that goes in the exponent up here. The camera's still pointing way over there. I shouldn't have started on this board. What can you do? The screen is in the way, so I can't jot on that board. So for the most part, think about gamma as the squishiness of the gas. So it is how many degrees of freedom you have to dump energy into the gas. So if you have a lot of degrees of freedom to dump energy into, so when you have a gas, the energy is in the random motions of all the atoms plus their rotational or vibrational motions. And if you have a lot of degrees of rotational and vibrational moments, then gamma gets larger. Typically, it's for just neutral atomic hydrogen, it's 5/3. For diatomic hydrogen, it's 7/5. Yeah.
Just checking, but this is an electronic equation, right?
Yeah,
Okay.
that's right. Although when you get a similar thing through Lane-Emden, and this is the thermodynamic version, and not the one you get out of Lane-Emden, which has the same flavor for basically the same physics, but you come about it in a different way. Does that help? That might make things more confusing. Yeah.
Can you define adiabatic real quick?
Yeah, adiabatic. Adiabatic means two things. Well, okay, it means one thing. It means no entropy change. So it means that the entropy is constant. But it is equivalent because now here we're getting into things that you haven't maybe learned yet. ds is dq over t, which if you've taken thermo, you've seen that. And if you haven't, don't worry about it. But basically, entropy change is just heat flow. So adiabatic means the entropy is constant, or it also means that heat does not flow out. Because of this relationship between the entropy and the heat flow. So when I say I do something adiabatically, usually that means it happens quickly relative to the time for the energy to leave the system. So if I compress a gas really fast, that's pretty typically adiabatic because it's too fast for the heat to escape. But if I compress it slowly, I can usually do that isothermally because I can do it slowly enough for the heat to escape. That makes sense? Or if I have it really well shielded, then heat can't escape. So sound in space is an intriguing concept, and this is something that I work on professionally to make stars. Also, why is the corona hot? The corona is hot because of magnetic reconnection. So we have this weird problem where we have this sun, and it's 6,000 degrees, and then the atmosphere above it is 1,000,000 degrees. How do you heat something to 1,000,000 degrees with something that is 6,000 degrees? You cannot. You have to have some other physics. So the other physics is magnetic reconnection, which we'll talk about later. And what is the solar wind? So the solar wind, and I'll talk about this today, when you go through and say, what does the atmosphere of the sun look like, you get that the pressure doesn't fall off to infinity. So either you need some pressure at infinity, or it can't be hydrostatic. That's the answer. So the answer is that it can't be hydrostatic, so the stuff has to come off because there's not a lid to keep the heat of the sun. Or there's not a lid to keep the atmosphere on the sun, so it's just constantly being produced and blown off. Okay, that's it for questions. Does anybody have any other questions from the reading that I didn't get to? I might have missed one or two, and I apologize. Please just
I just want to say I asked the Euler universal Lagrange
Okay.
question, but you answered it last class.
Sweet. That is part of what I try to do, is make sure that I bake in most of your questions into when I'm lecturing, so that it's in context. Okay, so what am I talking about next? I'm going to talk about real quick. I'm going to talk about the von Karman street. So I'm going to show you later. Uh-oh, that looks terrible. Sorry, my cameraman is drunk. There you go, that's better. Okay, so it's terrible still. It's slightly better. Okay, so one thing I'm going to do in a minute, and you've read about in the reading, is flow past a cylinder. So if I have, let's say, because I can, let's say my flow is downwards here. That's because I have that space to work with. And I have a fluid that's coming along and going around the cylinder. And we do this with some cube math and some cube boundary conditions. And I'm going to go through part of the math and leave the rest of it for you guys. What you find is that the flow comes in, moves around the cylinder, and then exits without any kind of disturbance or within any kind of symmetry breaking. Yeah.
Does that apply to all velocities, like no matter how fast the flow?
That's where I'm going.
Okay.
So, yes, but you can't tell that from the math, and that's one of the cool things about, or one of the hard things, or one of the interesting things about hydrodynamics, is this breaks down pretty fast. So what you find is you say, okay, what is the force from the fluid on the sphere? And you get that the force is just equal to the mass of the cylinder plus the mass of the water it displaces, for whatever, times du dt. What does that mean for dissipation? This means that if you're moving at a constant speed, there's no dissipation. F just equals ma, and that's it. So if the flow is constant, then there's no net force on the sphere, on the cylinder. Now, if you've ever taken a pool noodle and tried to drag it through water, you know that there's a lot of force. So where does that come from? What happens, and this is what Jake was getting at, is as you increase the velocity, really as you increase the Reynolds number, and the Reynolds number is this relationship. The Reynolds number is LV over nu, and I haven't defined nu yet. It's the viscosity, but we'll get to what that is in a minute. When this gets large, then things break down. So things break down in this way. and it's called the von Karman street. Let's see. I don't know. So it looks like this, and this kind of comes up. So you can see it starts to wag its tail like a dog and produce these alternating left-going and right-going pools of vorticity. So as you turn the velocity up, there's a critical velocity, and if you could predict what this critical velocity is, you will be famous forever. There's a critical velocity at which it starts to do this, and here is this is a set of liquid flow experiments where they have water flowing down a chute at different velocities, and they have a die that they put in the middle of the water so that you can see what the flow is doing. So in this top one, the die is straight because the water's flowing in this direction, and it's moving in a laminar fashion because the velocity is slow. But as you increase the velocity, then you start to get these wiggles. A little bit of velocity gives you a little wiggle. More velocity gives you more wiggles. And as you increase the velocity, you get more and more wiggles until you get to the bottom of the image, which is just turbulent craziness. So this doesn't have any structure to it anymore. So flow around a cylinder is very cool because it exhibits this fascinating process of spontaneous symmetry breaking. So there's a symmetry here, and this is a symmetry of the flow. Like when you actually sit down to solve this, it's a symmetric problem, and it doesn't care about the velocity. But clearly nature does in some way. And this is one of these von Karman streets seen from the space station. There's an island here, and there's a wind blowing this way down past the island, and you can see it launching these alternating eddies of flow. There's a lot of pictures of this. Like this shows, this is not a rare event. It happens on the regular. So this connects this potential flow, which I'll do kind of quickly in a little bit. But the interesting bit about this is when it breaks. Okay, the other thing that I'm going to do okay, so this is potential flow, which we'll talk about more a little bit later today. Since I have the screen down and the everything has to go away. Since I have the screen down, I'm going to show you this other thing. Oh, this is my paper. I have, we blew this thing up with a huge laser to see how stars form. It's really cool. I'll talk to you about it later. And I don't need you. There you are. Okay, so this is, and I forget which one is which. There's two of them. So this is content that was produced, probably 10 years ago now. 8 by this YouTuber physics girl, and yeah. And I'm just going to kind of throw this up because her graphics are, because it's fun to watch.
Check this out. I'm just going to drag this plate through the water in the pool. That's it. But look what forms. Perfect black circles on the bottom of the pool. And it's so weird. They don't die. They just keep going right next to each other. I sped this footage up because the circles took 3 minutes to cross the pool and didn't seem to be dying out. These got sharper as they went and made it all the way across. So cool. And look closer. You can see what's causing them. There are 2 almost unnoticeable dips in the surface of the water. Why don't they die out? And how do these dark spots form? And why do the dips move together? So many questions. Let's first look at what they are. When I drag the plate through the water, you could see it forming little vortices like you get when you move a paddle through the water. A vortex is a gas or liquid moving in circles with what we call a vortex line going up through the circles. They are everywhere. Tornadoes, water flowing down the drain, hurricanes, or the movement of air over an airplane wing. Vortices often form when there's a difference in fluid speed, like Okay,
so this is vorticity, which I just wrote up there, curl V. How much else do I want from this video? So I just like her first here.
Goes from one end to the other, and you can see the entire half ring.
This is actually cooler. It's cooler in this other. Yeah, it's this one. So okay, so what it is a half a vorticity dipole. So you put the plate in the water and you drag it through, and the edge produces vorticity, and then you have this thing that's spinning around. And because of Kelvin's circulation theorem, which is the thing that we're going to prove today, that thing is really, really stable. That's a stable object. And more importantly, you can flow along the vortex line. So here, this is really cool. So she puts the plate in the water and drags it through and then produces this thing. And you can put food coloring in one end of it and watch the food coloring. Let's see, I don't think I need all your music.
I made a video recently on one of the simplest but most mesmerizing phenomena I've ever discovered. You drag a plate through the water, creating two dips on the surface, and sunlight shining through the dips will create two crisp black spots on the bottom of the pool that can persist across the length of the pool. But the dips in the water are just the tip of the iceberg, as they say. Underneath the surface is an entire half-ring vortex, aka a toroidal vortex. I had never seen these before, so there's so much more to explore, and I know not everyone else has a pool, so I took some of your awesome suggestions and I'm gonna try them out. For this one, I have to get in the pool. I know I look ridiculous, but this is not warm. You can see here as the food coloring is dropped into the dips. The best part, I think, are the reflections you get off of the surface.
Here, this is a reflection, but you can see the two sides of the vortex of the flow coming in. And
I couldn't see what I was filming, but this just looked way better than I could have imagined, so we tried two in sequence.
Okay, so
The red one cut the green one in half. The red one didn't die, but the green one kind of disintegrated. It was cool. And of course it runs into my camera and dies.
So, okay, so I'm going to talk about more about that in a minute. Was that? Fascinating. What is still playing? That was very good. Yeah, I think so.
Dr. Collins?
Yeah.
Do you guys do that at the open house?
No.
You've got to.
Yeah.
You've got to figure it out. A little kiddie pool or like a tub. Maybe in that fountain right there.
Oh, yeah.
Right?
Sorry, now I'm thinking about that.
It's so fun. That's so cool.
I know, it's really cool, isn't it?
Yeah.
And her videos are great. I would recommend them. She unfortunately is not making content anymore because she got sick with long COVID and has not made anything in several years, which is a real bummer. Come on, turn on. I don't want the light in my eye. Hold on. There you go. Okay, so let's talk about the pool vortex thing first because it's freshest on your mind and most complicated. Am I just going to jump into that now? Yeah, let's just do Kelvin now. Let's just do Kelvin's circulation again. So we'll come back to this guy in a second. Oh, there's a reading up. I put a reading up just a minute ago, like right before class, due next Monday at the end of the day. Chapter 5. I think I'm going to start chapter 5 on Thursday, so the reading is a little bit behind, but that's even better place for you guys to ask questions. Okay, so Kelvin's circulation theorem. What does it say? It says that d by dt of the integral of omega dot dA equals 0. And this is important. What this says that vorticity is kind of conserved. This means that it's conserved, but only in, so the time derivative of this thing is 0. But this thing is only the area and not the volume of the vorticity. So what that really means is that when I have a vortex line, which is stuff spinning around like this, material can flow along the vortex line just fine. Because, I mean, the material has to be spinning, so it's a little spinning bit of stuff. It can spin and slide up this way or slide back down this way, or slide all the way along the flow. This is going to be more important when we get to magnetic fields, because this behavior, when you have the pool and you have the vortex here, and you put the dye in the pool in the vortex, you can watch the dye travel along the vortex. That's exactly the same math, though very different physics, as having a huge magnetic field on the sun and having material constrained to move along the magnetic field, because the magnetic field and the vorticity obey an identical evolution equation, which is kind of magic, which is why I can teach it in this class, because it's really the same physics. So let's go through, so that's what this means. This means that in an area sense, omega is conserved. So if I look at a cross-sectional loop that follows along the flow, then the vorticity in that loop is conserved. But I can move that loop along the vorticity line. As long as I don't go across the vorticity line, I have the same integral here. The same omega dot dA is going to be the same everywhere along this vorticity line, everywhere along this half vorticity loop. So let us go. So the first thing that we need, I need to not erase that part because that's the important part. D by dt. So we have two ways. So sorry, my brain just totally wait for a second. So there are two ways we're going to do this. The first way, we're going to use that omega equals curl of v, and in the other way we're not. The important thing is that when I do this derivative, both the quantity and the thing that I'm integrating over are going to move in time. So dA, which is my little element of vorticity, is going to move with time. So I have to do product rule on this and this. So let's do it using the way Landau and Lifshitz do it. So what they do is they first use omega equals curl of v. They also use that dv dt, the full derivative is minus 1 over rho grad p, and this is minus grad h, where h is the enthalpy. I talked a little bit about that last time. Stop me and make me go through it if you want me to see it, if you want to see it again. But the enthalpy is just like the internal energy plus the opportunity cost of getting that stuff there. So it's like the work that you need to put that material there plus the energy that it has by itself. So it's so the way this works, so I expand this out and I get d. The first thing I do is I say that this is equal to, we're looking at the d by dt of integral of curl v dot dA. We're going to use Stokes' theorem to turn this into an integral along dl. So this becomes the d by dt of the integral around the closed loop of v dot dl. Good? So now we split this into two parts. So we'll get the integral around the closed loop of dv dt dot dl plus the integral around the closed loop of v dot d by dt of dl. Everybody good so far? You want to say something again, or you got it?
Can you
get that last?
So this is just, it's just product rule.
Or you're taking the time derivative.
Yeah, so we take the time derivative of this part, and that's this one.
Yeah.
And then we take the time derivative of this part, and that's this. Does that make sense? So, then we just show that both of these are 0. So for the first term, let's keep it in orange. dv dt is minus grad h. So this is the integral around a closed loop of grad h dot dl, which is just h evaluated at the endpoints, h at a and a, which is just 0. Give that is just, I'm just integrating a full derivative, which gives me, since I'm going around a closed loop, gives me the integral on the endpoints, and that is the same thing minus the same thing. And this one, d by dt of dl is the integral of v dot d by dt of, dv. So I take this d by dt and pull it inside this little tiny differential of d. This is just like swapping the derivative order. So I have d little l dt, and that's just the velocity. So this is just the integral of d 1/2 v squared. So I'm just undoing a product rule. And this, again, is the integral of a full derivative around a closed circle at the endpoints. And so this guy is also 0. Oh, yeah. I don't know, because that's also the camera. Yeah, I can. Is that better? Okay. So now this isn't a general enough proof because we use this, and when we get to ENF and when we get to MHD, we don't have an analog of this. So I'm going to go through this much grosser derivation. That's really pretty similar, but you got to do more vector calculus. So I'm going to go through it because the book goes through it, and we're going to need it again when we do MHD. So we do the same thing. We break this into a product rule so that we have a d by dt of omega dot dA plus the integral of omega dot d by dt of dA. Right? And this term is easy because we found out that this is just del cross v cross omega. We found that from taking the curl of the Euler equation and going through some stuff. And we're left with this. For this term, we have to sort out what d by dt of dA is. So what does this look like? So I have some vortex line, and I have some dA1 here. That dA is then carried by the fluid to some new position, dA2. And what I want to know is, what is d by dt of dA? So we know that from calculus, this is just dA2 minus dA1 over dt, whatever dt happens to be. This is just the definition of a derivative, which is kind of dumb, but really, as a physicist, it took me a long time to realize that you just need to go put in the definition of the derivative a whole bunch of times in a whole bunch of places, and everything makes sense. When you start doing it on a computer, this becomes really important because this is how you do everything. So what is this? So what is dA2 minus dA1? That is this little guy minus this little guy. Okay, here's the complicated stuff that really takes a minute to get your head around. If I take a closed surface and I integrate just the outward normal of that surface, I get what? What do you think that's going to be? I just add up all of the outward normals on a surface. You could think about this as, say you got a basketball with pins pointed out of it. That's the outward normal everywhere. If I take all of them and I add them all up, I'll still get a vector, but what is the value of that vector? It's 0. Why? Because every time I've got one of these, I've got another one of these, and they cancel out. So by the symmetry of the problem, this winds up being 0. Another way to think about this is what we're saying is the integral of dA, right? This is all I'm talking about, just the integral of dA. Remember, dA is an outward normal. This is equal to the integral of 1 dA, which is equal to the integral of the gradient of 1 dV by Stokes' law. Does that make sense? Now this is some vector 1, but whatever. What's the gradient of a constant? 0. So this equals 0. So what we need to do is we need to take this surface, and we're going to make a little volume out of this. So now I've got a little can with dA2 at the top and dA1 at the bottom. And remember, what I'm looking for is the difference from dA1 and dA2, the difference between those two. That's what's going to give me how dA evolves in time. What I'm going to use is the fact that the outward normal around this whole thing is 0. So I can say, what is the outward normal around the whole thing? It's going to be dA2 plus dA1. Uh-oh. Those point in the same direction when the fluid is flowing. But when we're talking about the outward normal, then we need to change the direction on this normal. Is that all right? So now I have dA2 minus dA1. This is, now we're talking about the total surface area, which I'll call sigma, plus whatever the outside is. So how do I sort out what the outside of a cylinder is using calculus? So we say that when if I have a line, so what is the length of this? The length of this is going to be V times dt. It's going to be my tiny little time difference between those two things. So the length of the side is going to be V dt. So the total area is going to be the integral of V cross dl around the closed circle. Because if I have a rectangle that looks like dl on one side, that's the dl going around the edge, and V dt on the long side, then the area of this is the area of a parallelogram divided by two vectors is their cross product. That's just a geometry thing that you probably learned but maybe forgot. I totally forgot. So the total surface area of this is dA2 minus dA1 plus, and if you actually do the vectors right, you get a minus V cross dl. So d by dt of dA is equal to minus V cross dl. Does that make sense? Maybe, maybe not. So I've got this thing, I've got this can that's evolving through space. This is dA1, this is where I start. This is dA2, this is where I end up. I know that dA1 plus dA2 plus the surface equals 0 because they're all pointing outwards. And then I got to doctor this because actually the way I draw my dA1 is pointing inwards. The surface on the outside, so this is the wrapper of the can, as it were. This is the integral of V cross dl because this length is V and this side is dl. So d by dt of dA is minus V cross dl. So now we go back to here. And we have to do a little bit of algebra with this. So what we have is the integral of omega dot d by dt of dA, which we're now going to write, and this is an integral over the surface dA. We're going to turn this into an integral over the curve bounding dA of omega dot v cross dl. I just plug this into there. Now we have a couple of triple product identities. So omega dot v cross, if I have A dot B cross C, that I can just switch these three things cyclically and get C dot A cross B. So I'm going to do this, and this turns into the integral of omega cross V dot dl. Okay, so it's just a vector out identity stunt. We're almost done. So now I'm going to take Stokes' law, because now I have these two terms. So my first term is the integral across the area of curl of v cross omega. The second one turns into this. I'm going to use Stokes' law on this, and this turns into the integral of curl. This is an integral over the curve. Now we've got an integral over the surface of omega cross v dA. And there's a minus sign that you pick up when you do this triple product. And then this term is curl of v cross omega cross v, v cross omega. And this term is the integral of curl of v cross omega. So we get the same term twice, so we get a 0. Yeah.
So it should be v cross omega dot dl, or?
Yeah, so you need a minus, so when we get here, it's the curl of v cross omega dA.
Okay.
Because the curl comes from the fact that we turn this dl into a dA with Stokes. And we pick up the curl. So the stunt is this three-dimensional calculus stunt where you've got to draw this can in your head. This is a pretty general proof. There's an even more general proof that I like actually better, but it's grosser, and 2 of these is enough. Does anybody have any questions about either what does this circulation theorem mean, or how do we get there? Everybody all right? Yeah.
I guess I'm more wondering what it means in the context of this differential area, is the actual area is not changing, or can it change when the omega is changing?
Oh, my little d?
Yeah.
Yeah, that'll change too.
Okay.
So it'll change in its size as well.
Okay.
But we don't need to worry too much about the fact that the top is bigger than the bottom, because the whole thing has to add up to 0, whatever it is.
Okay.
So you could have something that flares out a lot, but then that just is taken care of by the geometry, because everything has to add up to 0 regardless. Okay. Potential flow. How am I on for time? Oh yeah. Oh, I have plenty of time. Great. This winds up being incredibly important and very, very useful. So we'll use this theorem when we next week talk about how airplanes fly. Okay, so this is the full existence of Navier-Stokes, or of Euler's equation. But one thing you want to learn how to do as a physicist is how do you throw crap out so that you can solve a better equation or a simpler equation. So we start with d by dt of v plus v dot grad v equals -1 over rho grad p plus whatever forces I'm going to put on the fluid. So this is Euler plus a force. And what is wrong with this right now? Very important that that's a partial t. In the previous derivation, those are all full derivatives because the surface is moving with the fluid. the Lagrangian derivative, the partial derivative, is fixed with respect to the fluid. So dA, so if I had said partial t of the integral of omega dot dA, this is a simpler expression because it's the partial, because that's holding dA fixed. So here, if I was writing this down, then I would just be left with d by dt of omega dot dA, because by definition of the partial derivative, you're holding space fixed, so that you don't get another term. But if I have the full derivative of the same, of omega dot dA, that is d by dt of omega dot dA plus the integral of omega dot d by dt of dA, because it's the full derivative. The full derivative moves with the fluid. Okay. So we have this, and we can throw stuff out. So this is the full derivative of velocity with respect to time. So the first and easiest assumption that you can make is that the velocity is non-changing. So our first assumption is that the full derivative of the velocity is 0. So if the full derivative is 0, then this goes away and this goes away, and we're left with 1 over rho grad p equals whatever body force you put on the system. Which throws out all of the interesting stuff, but that's all right. We get an interesting solution. So the first thing that we want to do is the dumbest thing possible, and that's just a 1D constant temperature situation. So if the temperature is constant, then I can say that P equals rho T times K over M. If it's an ideal gas, I can say this. If it's constant, then this temperature is simple to deal with. So I'm just going to, I forgot to set the system up. What does our system look like? So we have a one-dimensional atmosphere where we have gravity that's pulling down, and we're going to set up a pressure gradient that opposes gravity. So F is just going to be rho g in the z hat direction. No, I'm sorry. F is just going to be g in the z hat direction, because this is the force per unit mass. So I can say that grad P equals rho g minus rho g in the z hat direction. Are we good with that? So dp dz equals minus rho g. I'm going to take all of this and plug it in here, and we're left with t k over m times d rho dz equals g rho. And g comes over here. I'm going to take all these things and put them over there, and I'm left with d rho dz equals g m over k t times rho. So this is an equation that you all should just be able to integrate in your head. So what's the solution to this? And if you can't, we'll talk about it in a second. We'll talk about it in a second when we do it. So I've got a thing that's whose derivative is proportional to itself. So let us solve this. The way I solve this is I just remember that it's an exponential, but let's actually get that. So let's solve this real quick. That's awkward. Sorry about the video. So d rho dz equals, I'm gonna call this stuff here 1 over h. I'll show you why in a second. So this is equal to 1 over h times rho. Looks like so I'll put this dz over here and the rho over here, and I'm left with d rho over rho equals 1 over h dz. And now I have basically full derivatives that I can integrate, so I can integrate this and I can integrate this. What's the integral of 1 over rho? Everybody? Log rho. So this is log rho equals 1 over h equals, we integrated z over h. So rho equals my boundary condition, e to the minus z over h. I dropped a minus sign somewhere. whenever, so this is a differential equation that you should bake into your brain because it shows up all the time. And is really one of the most important things that we do in physics. So whenever the time rate of change of, or whenever the change of anything is proportional to itself, you wind up with an exponential. And rho naught is the value at the boundary that you pick, wherever the boundary is. And so here we see that this h is the scale height, because if I double this, so my density as a function of z falls off exponentially. If I double the scale height, then this falls off half as fast, and I get something that looks like that. So if I look at where, wherever it's half of its initial value, I get basically the scale height. So, or I get what we call the scale height of the gas. So that's effectively how thick is the gas. Well, it's about where it falls off to half of its original value. Does that make sense? Does anybody have any questions about a 1D atmosphere? So this is how you can treat the atmosphere close to the surface of the Earth. And it's a relatively straightforward derivation. Let us now try it in 3 dimensions. 1D with a constant temperature gives us an exponential. Let's try 3 dimensions with a not constant temperature. So let's assume that so then we're left with, oh, now here's where my memory runs out, and I got to look at my notes because otherwise I'm going to screw something up. So if we get the same starting equation, we get dp dr equals 1 over rho minus 1 over rho dp dr equals f. If I have now a star with an atmosphere, then the force is equal to minus g m over r squared. That's just Newton. Apologize again about the movie. But this is for discrete things. So we're going to change this up, and this is going to be g m of the star times rho of the little parcel of fluid that is sitting at that spot who is feeling gravity. So now my this is equal to minus g m over r squared. This is the acceleration. I put the density over there, and I plug in the ideal gas law, and I'm left with dp dr equals minus p over t times k over m. This comes from the rho that's right here, times g m of the sun over r squared. And t, what can I say about t? So remember last time we said that the thermal gradient is k dot grad t equals the thermal luminosity. So if we just say that we're in hydrostatics, then this has to be constant. If we're saying that it's static, the net flux has to be 0 of heat. So here we're just going to invent this. K, this is the thermal conductivity in a plasma. This is some constant. We'll call this kappa times t to the 5/2. We'll prove this later. Actually, we won't prove this later, but the proof is in the book, but it's a little heavier than we're going to get because it requires most of Maxwell's equations to get there. So our thermal conductivity goes like t to the 5/2. So we can solve this in cylindrical coordinates, and you get that the temperature is going to go like the temperature at your surface times r naught over r to the 2/7. So you just solve this and you get that. And I plug this into here, and I do some ick math, and you're left with the solution that P equals P naught times the exponential of, let's see if I can get this all right, 7g big M from the sun, M mass of the proton, over KT T naught times R naught times R naught over R to the 5/7 minus 1. So the important thing is that as R goes to infinity, so where this comes from the algebra, but as R goes to infinity, this term falls away, but we're left with a non-zero pressure at infinity. So what that says is that if I've got a spherical star and there's some temperature source at the center, temperature is going to fall off, but you have to have some pressure at infinity to keep the wind static. So the fact that the pressure at infinity is just this part is a consequence of the fact that we assumed that dV dt is 0. So if you assume that dV dt is 0, then the sun has to have a pressure keeping it in, or stuff has to be leaving the sun. So those are the two options. So either this is wrong, or this is wrong, because this is a natural consequence of this assumption. So what that means is that there's a wind blowing off the sun, and we can measure this wind, and we sit in it. And it actually is the solar wind is the reason why there's no atmosphere on Mars, because the solar wind is a charged plasma, and that plasma streams past Mars. Mars, having no magnetic field, has to take all of those charged particles in the face, and all those charged particles strip off the atmosphere. The Earth has a magnetic field, and that deflects most of the solar wind, which lets us keep our nice atmosphere intact. Okay, so that's what I have to say about hydrostatics. It's two different atmosphere models. Does anybody have any questions about that? Or questions from the reading that I forgot to get to? Everybody happy? Okay, and then I've got 12 minutes left. I could do steady flow, and then I'll be done. Okay, let's start with this equation again. And now, we're not going to throw this term out, we're just going to throw out this term. So there is an acceleration of the flow, but it's fixed in space. What does that actually mean? So that means, like, if I have an infinitely large reservoir with a hole on the side, water starts up at the top with 0 velocity. By the time it gets here, the velocity is not 0, and then it comes out and hits the ground, and the velocity is 0. So say I've got a swimming pool with a hole in the side. The swimming pool is effectively infinity, unless I'm standing there for a really long time. As I hold space fixed, the velocity doesn't change. So if I pick a point in space, the velocity isn't changing. But as I move through space, the velocity changes. And that's the difference between these two terms. So this is the fixed in space term, and this is the moving through space term. That is the acceleration of the fluid. So we'll just have this one. So let's deal with that. Let's deal with that equation real quick. So one of my favorite vector identities, grad A dot B equals A cross curl B plus B cross curl A plus A dot grad B plus B dot grad A. So this is a vector identity that you solve with the Levi-Civitas symbols and some identities with the Levi-Civitas. But if A and B are the same, then I'm left with div A squared equals, I'll have two of these, 2A cross del cross A, plus 2 of A dot grad A. I replace this with v, and I'm left with the following. This term turns into 1/2 div v squared minus v cross del cross v. There's a half in front of that one too. There's too many parentheses here. So getting rid of the partial derivative, so now we're in steady flow, not static flow, just steady flow. This term turns into 1/2 grad v squared minus 1/2 v cross grad cross v equals, let's put everything on the other side, plus grad p over rho plus grad phi. Because we're going to say that our force is conservative, and so I can always write my force as a minus grad phi. So does you guys have seen force as minus grad potential in mechanics, yeah? Right, so that's pretty happy. We can do that a lot, and we like to do that because it makes this vector turn into this scalar. So that's pretty handy. So now we're going to integrate, we're going to do an integral along the streamline. So what's a streamline? A streamline is a vector field that is everywhere parallel to the velocity of the field. So it's just a flow that follows the velocity. So if my velocity starts up here, it comes down here and goes out this hole, I'm going to do an integral along this whole integral. So I'm going to integrate along dl of 1/2, or let's pull that 1/2 inside, grad 1/2 v squared plus, oh there's a minus, minus v cross del cross v plus grad p over rho plus grad phi. We're integrating all of this dot dl. Does that make sense? So this is just, I put everything onto one side. I know that the inside equals 0, so the integral has to be a constant. Where's 0? So, no, the integral has got to be an integration constant. So when I integrate, let's start with this term by term. So this first term, I've got an integral of a full derivative. So that's just 1/2 v squared evaluated at the endpoints. This second term, let's talk about this second term. I have dl dot v cross del cross v. What can I say about the relationship between this whole thing and v? I got v cross something. It's a product of v, but that doesn't matter. It's some other vector field. V cross some other vector field is perpendicular to v, right? So this is perpendicular to v, so then it's also perpendicular to dl. Because by definition, dl is always pointing along dv, because that's how we've defined our streamline, right? So what is dl dot something that's perpendicular to dl? 0. So this term is cool, this term goes away. Getting rid of the complexities in this term is kind of half of what we do. And then this term, I talked about it already, in an incompressible flow, density is constant, so this comes out, and we're just left with plus p over rho. And then this is again the integral of a constant plus phi equals, we'll just call that a constant. So you can think about this as integrated at the endpoints, or you can think about it as the total that's got to equal a constant. So this is Bernoulli's equation for steady but not static flow. And this is very cool because you can do all kinds of things with it. You can figure out how fast water is moving at the bottom of a waterfall. You can figure out how fast water comes out of something when you stomp on it. Okay, I got 5 minutes left, but I ran out of things to say. That's not true. I could talk literally forever. Mm-hmm. But I've run out of content that I want to present. Does anybody have any questions about any of these things? So we had talked about von Karman street, pool vortices, Kelvin's theorem, potential flow, hydrostatics. steady flow, yeah.
Is it possible for us to put like the computer to the side? Because I think like over there, I have the flash can't see over here. I know.
Oh, yeah, and this is just in the way?
Yeah. I can't see that whole bottom corner.
Okay, yeah, and it doesn't show up very good on this screen either. I'll fix that next time, yeah.
Or maybe like just writing on the top.
Yeah,
And the dog pass with the boards are fine.
yeah, I'll figure something out next time. I'll do something better.